Welcome to this lecture in the lecture series by the Applied Statistics Group at Aalborg University. And this is part of the series about ANCOVA, analysis of covariance, where we'll consider what's called an additive model, and we'll look in more to details about that. And analysis of covariance is where we have a quantitative response variable we want to predict with both quantitative and qualitative predicting variables. We'll start with briefly recapping the data and hypothesis that's been presented in a previous lecture, and then we'll look at this ANCOVA model where we have this called the main effects only on additive model. So we are looking at three variables: the annual income, which will be our response, years of education, which is one of the explanatory variables, and the race, which is the other explanatory variable. And race has three different levels: black, Hispanic, or white, and we can recode that using dummy variables. And when we have three levels, we need two dummy variables, Z1 and Z2, as previously explained in another lecture. And here's a brief overview of what the data looks like, and we have 80 different individuals in this sample. And the kind of hypothesis we could be considering with this data is something like: how is your income related to your education? How much can we expect the income, your annual income, to increase for every year you have a further education? And in this additive model, we first consider the model without interaction. So this is what it means that we have an additive model or main effects only. What we do is that when we have recoded the race with the dummy variables, then we have all quantitative variables x, z1 and z2. z1 and z2 are special, but they're still numbers, so we can use them in mathematical equations. And we'll make a standard regression, as you've learned about previously in the course. So a standard multiple regression where we say, well, there's the mean value of the variable y is a linear relationship with the explanatory variables. So this is the main relationship we have between the variables, and it's linear. And if we look at what does that really mean due to the special nature of the explanatory variables Z1 and Z2, well, then we can really think of three different cases. When we have a white person, well, then Z1 and Z2 are both 0. And when they're both 0, then all what remains in the equation is the intercept alpha and the slope beta of the education. If Z1 is 1 and Z2 is 0, and then we have the case of a black person, and the expected annual income for a black person is then that we put Z2 equal to 0, so that part goes out, and we have that Z1 is equal to 1, so really we get that we have alpha plus beta times x if we use the equation directly up here, and then we have plus beta 1 times 1. Remember, we have a black person, so Z1 is 1, plus beta 2 times 0. So this is coming from here to there, and then of course this is 0, and beta 1 times multiplied by 1 is just beta 1, and that's how we arrive at this. And then in the exact same manner, if we put Z2 equal to 1 and Z1 equal to 0, then we get this expected relationship between the income and the years of education, given that it's a Hispanic person. And then if we look at these equations, we can see that the difference between the equation for whites and blacks is simply the constant factor, constant term, beta 1. So for any value of x, the difference between this equation and this equation is beta 1 all the time, right? So that's the only difference between. So always there will be a difference between these two of beta 1, and this. So that's when we compare white and black. And if we compare Hispanic and white, well, then there's only the beta 2 term that's different. So that's the interpretation of the parameters, is that beta is the slope of the variable x, so that's of the years of education. Alpha is the intercept, that's where everything starts when everything else is 0. And then beta 1 is the difference between the income given the value of the education, the difference between the income of a white and a black, and beta 2 is the difference from white to Hispanic. And if we look at it graphically, it basically means that the model we've suggested that we claim is describing this data is that we have 3 parallel lines. So the slope of each line is beta. So we have the line here that was for whites, right? And that was the equation was alpha plus beta x. If we take the slope for, or the line for Hispanics, then it was alpha plus beta 1 plus beta x. So the distance here, the vertical distance here, is equal to beta 1. And finally, when we look at the green line here, the green line is for the blacks, and one has alpha plus beta 2 plus beta x, as we remember. Well, so that means that the distance anywhere, because they are parallel lines, the vertical distance is the same anywhere on the x-axis, is this beta 2. And yes, so that's, and this is a model that we have claimed, right? There's so it's a postulate for whoever is building a model or describing the data, is to say, well, there's these 3 parallel lines, and then later on we could make an investigation whether are these really significantly different, or should they really have different slopes, etc. The model we've proposed so far is imposing this condition, and it's giving us 3 different lines, and then we can ask software to fit these 3 lines. So these are theoretical lines, and then where do we actually put them? What's the optimal place to put them? Well, we use the least squares criterion, saying, well, you should put these 3 lines so that the squared deviation, vertical deviation, is as small as possible when you sum it all together. So you compare all the green points with the green line and look at the squared distances vertically. You compare all the red points with the red line, and so on, and square them, and then you compare all the blue points with the blue line. And then you choose these 3 parallel lines. You can shift them up and down, and you can change the slope of them as you like. So you have 4 different things to change, with 3 intercepts and 1 slope. And then the computer decides, using this criterion, what is the best configuration of the parameters. And then you get an output, and that's what we have here with 4 different estimates. This is like a typical output table from statistical software. In this case, it's based on results from R, but any other software will give you a similar type of result. And we look at this column with the estimates, where we say that the prediction equation for y is that y is equal to the estimate plus the estimate of beta plus beta 1 estimate times, sorry, not x1 but z1, plus beta 2 times z2. And in this case, that is y hat is equal to, so these are the ones that gives the minimum squared error, so it's minus 15.7 plus 4.4 times x, where h is the number of years of education, minus 10.9 times z1, minus 4.9 times z2 here. So we can do one for white. That's, we also call that the reference group, right? The prediction equation for white is 15.7 plus 4.4 times x. For say black, now I have to remember black is the second one. So you can see up here from the names in the table that it's set 1 is equal to 1 and set 2 is equal to 0. So we have minus 15.7 plus 4.4 times x minus 10.9 times 1 plus 0. And for the Hispanics, we then have the prediction equation minus 15.7 plus 4.4 times x minus 4.9, like this. And of course these can be simplified to say, well, minus, so this is 26.6, if my calculus is correct, x, and here we have minus 20.6 again, plus 4.4 times x. So we have these three parallel lines, here, 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 all have the same slope in the x and just have different intercepts. And these are the lines that describe the data the best as possible in terms of the least squares criterion. And this corresponds to that we see that the white is the one that has the highest starting point. Below white is the Hispanic, and finally the lowest one is the black. And if we go back to the plot, that also is what we are seeing here, that it's white, Hispanic, and black in the ordering. And notice how we get negative intercepts on the y-axis, and that's because the y-axis is, here we have the scale down here is such that 5 would be around here, and then you would go even further back to have 0. So if you continue the lines, they'll become negative. But that just means that we cannot use this model for very different levels of education than what we have in the data. So this is a model describing people with an education which is somewhere between, let's say, 7 years to 20 years of education. And the picture may be completely different outside that range, so we should only apply the model in that range where we fitted it to the data. Thank you for listening.